Here are two different types of diagrams. The one on the left is for what we call a Moore machine. The one on the right is a Mealy machine. And I have to tell you that the distinction is not hugely important, but they do have names, so I thought I would mention them. Here, the output bit, the output from the state machine, in our case the U bit, is associated with a state. Here it's associated with a state and a transition, so it is with a particular arc. And so those are, you can think of this in terms of the combinational cloud. You can think of the output being a function only of the current state or of the current state and the new input that's coming in. So it's not a big deal, but what is a bigger deal is thinking about what makes a correct state transition diagram. The first thing we should notice is that for any particular state, let's pick S2 here, I have to have, none of the arcs can have overlapping labels. Right? So in this case, we only have a single input. So that means that I would expect to find one arc labeled 0, corresponding to a 0 on that input, and one arc labeled 1. If I saw two arcs labeled 0, what would that mean? I think that's a great answer. We wouldn't, the statement, we haven't really been very specific enough, which transition does the state machine supposed to take? So that's a no-no. Right? You can't, the arcs all have to be mutually exclusive. It's pretty trivial on a diagram like this, where we have one input and just two labels for the arcs. It gets more complicated when you have a lot of inputs, and you have to make sure that none of the logic equations that you've written about, the logic function of all the inputs that determines whether that transition is the valid one or not, you have to make sure that they are all mutually exclusive. The second requirement is not only are you not allowed to have two places to go for any particular set of inputs in current state, you have to have at least one place to go. In other words, you have to collectively exhaust all the possibilities. So there can never be a combination of inputs in a current state where the state machine doesn't know what to do. You have to really figure out all the things for this logic to make sense. So that's it makes sense. It's easy to design machines where you forget to do it once in a while. Typically, the arc people forget is the arc when you stay in the same state. Right? They forget to say, and if none of my output arcs is true, but I want to stay where I am, well, that should be represented by an arc back to the current state and the appropriate equation for when you take that transition, because that information will also have to be reflected in the logic. Because remember, that next state calculation has to be accurate, even if it's producing the same answer that it produced for the previous state. If you leave that equation out of your logic won't do what you think. So you really need all those loop-back arcs as well as all the arcs from transition to transition. So here's our hardware. And this is, what I've done is replace the combinational cloud by our general purpose combinational logic device, the read-only memory, which takes in the current state and the inputs. In this case, there's 1 bit of input and 3 bits of state. Why 3 bits of state? Where did that come from? Whoa! 3 landed from the heavens. Why 3? Why not 2? Why not 7? Yes?
Because you need 3 bits to represent however many states you have.
So how many states did we have in the diagram? We had 5 states. How many different combinations can I represent in 2 bits? 4 combinations. Well, I have to distinguish among 5 different cases, 5 different states that I could be in. So 2 bits isn't going to do it. 3 does, right? So that's where that 3 came from. So, and 1 bit here. So this means that we have 4 bits going in. So I'm going to need 16 locations in my ROM, 16 rows in my truth table, and in each row I'm going to have to provide 4 bits of output, right? Which is 3 bits of next state and 1 bit of unlock. Okay, and for now, we're just assuming that in is nice. We're changing the clock only after in has become stable. We'll get to fixing that simplification pretty much next lecture, but for now, that's what we're assuming. Okay, so remember that this output can either be a function only of the current state or of the current state plus the inputs. Almost all the machines that we'll explore are the so-called Moore machines, where the output bit is strictly a function of the current state.